All right, so we are on Key Concept 10, and this is the first part, 10A. We are interpreting key features of graphs and tables. Learning goals for this target: I can identify how variables are related on a graph. I can identify the difference of terms to apply a rule to represent the function shown by a table. I can use information, not a information. I can use information provided in a graph to answer questions in a real-world context. And finally, I can identify whether a table indicates a function or not, and if it is a function, whether it will be linear or nonlinear. Okay. Terms to know. Difference of terms. It's either the common ratio, which is when you are multiplying or dividing. Okay, so multiply, divide. Common difference. Add, subtract. Or common operation in a function, meaning like if you square every time. Quadratic equation, it's a function where the x value will be squared each time in order to find the y value. Difference of terms. So if you have a common ratio or a common operation, unless it's addition or subtraction, that's where you will have a nonlinear function because the amount that your y value is changed by will be different every time. Remember that for a linear function, you have to be adding or subtracting the same number every time. So that would be a common difference. And finally, function, a mathematical statement that relates input to output. That was just a recap. You should know that by now. Okay, number one, example number one. How are the variables related on the graph? Well, all you have to do here is say, okay, as x increases, so as the number of tickets increase, this is always, whatever's on the bottom will always be increasing. It's your y value that could either be increasing or decreasing. So as this goes up, where are we starting and where do we finish? So we're starting here and we finish here. This value is higher than where we started, so that is increasing. So we say as the number of tickets sold increase, the cost of the tickets increase. So that's where you're looking at these here, the labels for each axis. All right, example 2, find the difference of terms to determine the rule which could represent the function shown by each table. So this is where you have to kind of go through and figure out what's happening each time. So here, I went up by 1, and then I went up by 2, and then I went up by 4. Okay, so I don't see a discernible pattern necessarily with that. So what you want to do is then take a look at your x values and say, okay, so out of these, okay, this is negative x squared. Are any of these values negative? Are any of these values negative? No, we can eliminate that. Is it exponential? Possibly, but it doesn't quite look like 2 squared would be 4, but then if you did a number to the third, yeah, it would have to be kind of like, it's a possibility. It's definitely a possibility, so we'll look at that one. X squared. So like if I square 1, will I get 2? No, so that's not the case there. 2 to the x power, possibly. 2 times x. Like 2 times 1 is 2, yes. 2 times 2 is 4, yes. Keep going though, just to make sure. 2 times 3, is that 8? No. Okay. 1 times 2, is that 1? No. Okay, so that can't be any of these. So let's focus on this. This one. If I do, well, we can start from the bottom. If I do 2 to the 0 power, is it 1? Yep. If I do 2 to the first power, is it 2? Yep. 2 squared is 4? Yep. And then just keep going to make sure, because as you saw with this one, I got all the way to the 4th term before I figured out it wasn't it. 2 squared is 4. 2 to the 3rd power is 8. Yes. 2 to the 4th power is 16. Yes. So this one, D, will go with that. A, let's start at the top now. 0 squared is 0. Yes. 1 squared is 1. Yes. 2 squared is 4. Yes. 3 squared is 9. Yes. Okay, and that works too. So this is y equals x squared. This is a quadratic equation because each time we're squaring our x value. This doesn't work. So finally that one goes there. Okay, so it's just a matter of trial and error going through the entire thing. Don't stop after a few because as you saw, E worked all the way up until this point. Third example, find the difference of terms to determine which rule could represent the function shown by each table. So we need to find the rule. So before you look at all these here, what you want to look at is the tables. So what's happening each time here? So how do we go from 1 to 1/3? Well, you could either say we divide by 3 or we're multiplying by 1/3 and just make sure that carries through. 1 times 1/3 is 1/3. 1/3 times 1/3 is 1/9. 1/9 times 1/3, so it continues to work. So basically, once you get past the first one, we're just keep multiplying that bottom number by 3. Top one stays as 1. So we're going to look for something that is multiplying. So we're looking for something that has a variable in the exponent and 1/3 as its base. You can see that C, before we get to that, so C does in fact match this one. This one, we are adding 1/2 each time. 0 plus 1/2 is 1/2. 1/2 plus 1/2 is 1. 1 plus 1/2 is 3/2, or 1 1/2, and so on and so forth. So each time we're adding 1/2, so C goes here. Now here we're looking for something that starts at 0. It's basically just 1/2 times x, because that when you have something where you're adding, that's where you're going to have this format, y equals mx plus b. Okay, we're adding 1/2. That's our slope, or our rate of change. Our y-intercept is 0, so we don't need to include it. So we're looking for y equals 1/2 x. So b would match up with this one. All right, fourth example. New York City tracked the temperatures on the first day of each month over a year. The cumulative frequency graph plots temperatures in Central Park over time. We want to use the graph to estimate your answers for A, B, and C. So what was the temperature in November? So we go along the line here. We say, there's November right here. Go up to here. And this is our point here. So we can look over to the side and we see that it's 60 degrees. But it's just an estimation, so we're going to say about 60 degrees. Temperature in May, do the same thing. Go to May. Go up. So we're in between 60 and 70, so we can say about 65 degrees. And when did the lowest temperature occur? So you want to look for the lowest point on the graph, which is right about here, which is close to February. So around the beginning of February. You could argue end of January as well, but either one of those answers work. Okay, so pretty simple. That's just reading the graph. And final example, would the tables indicate a function? And if so, would it be linear or nonlinear, and how do you know? This is where your difference of terms comes in. So look at your y values and see what the rate of change is each time. So here we add +1, then we add 3, then we add 5. Okay, so that one does indicate a function, because there are, as long as you have a unique x for y, you basically can't have the same x equaling 2 different y values. It is a function, so it would indicate a function. However, the function would be nonlinear because it is not increasing at a constant rate. These numbers that it's increasing by is not the same each time. Okay, we go to our second one. Okay, here I added 4, and then I added 4, and then I added 4. So now we are increasing by the same number each time. So it would indicate a function, and the function would be linear because it increases at a constant rate. Add by 4. So it's just a matter of looking, how are my y values changing, okay, in each case, and is it the same? And as long as you don't have like x equal, like a 1 over here that says -9, and then you would have another one that equals a different number, as long as you don't have that, you have a function. So just bear that in mind. And that is it for this video. You guys have a lovely day / evening or whatever. And if you have any questions, please ask me in class.